and gentlemen, welcome to the seminar for Astronomy and Particle Physics of Masterminds Masterclasses 2.0, in short, the MM2.0, organized by the Council of Hong Kong Laureate Forum, the HKLF. Allow me to introduce myself. My name is Tasha Zheng, and it's my great pleasure to be the MC today. On behalf of HKLF, I'd like to welcome everyone to this seminar who are joining us in person today, and we'd like to extend our heartiest welcome to our online audience who is joining us all the way from all around the world through the online webinar platform. Thank you for joining us. Yesterday, we had a grand launching ceremony and seminar for mathematical sciences. I believe all of our audience were excited to have intellectual idea exchange with yesterday's speakers. And today we're very honored to have invited three renowned scientists in astronomy and particle physics to share with us their captivating research. They are Professor Roger Blandford, who will be joining us from the US, Professor Chu-Ming Chung from the Chinese University of Hong Kong, and Professor Look Kam Bu from the Hong Kong University of Science and Technology, who are now joining us in person. There will be a Q&A section after each of their presentations for you to raise questions and exchange ideas with them. We welcome questions from both our in-person and online audience. For our online friends, feel free to use the Q&A function on the online webinar platform if you have any questions for our guest speakers. And to facilitate today's seminar, in particular the Q&A sections, we're very delighted to have Dr. Jane Dai, Assistant Professor of Department of Physics at the University of Hong Kong, to be our moderator. Ladies and gentlemen, without further ado, please join me to welcome Dr. Dai to take over the following sections. Dr. Dai, please.
Good morning, ladies and gentlemen. It is my great pleasure today to be the moderator of the event today. I'm Jane Dai, and the organizers asked me to do a little bit of self-introduction, and I would like to briefly talk about what do I do, and more importantly, my link to some of the speakers today. So I am basically a theoretical and computational astrophysicist working on general relativistic phenomena, and in particular the events in black holes and also in transient astronomy. And I also employ large-scale numerical simulations and random simulations on superclusters to conduct my research. So I would like also to show you a little bit of a story of mine. So I obtained my undergraduate degree from the Hong Kong University of Science and Technology and did my exchange program at Berkeley during the time. And at that time, I would like to mention at the end of my undergraduate years, I was thinking about if I should pursue a life in science. And I was debating whether I should apply for graduate school and apply for PhD study. So at the time, I was confused, and I approached Professor Ming-Chung Chu, one of the speakers today, to ask for his advice. And Professor Chu very nicely and kindly and patiently gave me many inspirations. And then I decided to apply, and fortunately got admitted by Stanford University. And my PhD supervisor is Professor Roger Blandford, the first speaker of today. So I learned a lot of astrophysics from Professor Blandford, and more importantly, he has taught me how to be a scientist. And this is an old photo of Roger and me when I received my PhD degree from the Stanford University. And afterwards, I have got my training as a postdoctoral scholar at various universities in different continents. And then I became a faculty member first in Denmark, and 3 years ago, I moved back to Hong Kong. So this is a short story of mine, but I would like to mention that it has been a great pleasure for me to interact with these masterminds which has inspired me a lot. And I hope that through the event today, the students here would also be able to interact with these three great scientists and got inspired to pursue a life and career in STEM. Okay, thank you. So without further ado, let's start the talks today. So first, I would like to introduce Professor Roger Blanford. It is my great pleasure today to introduce the first speaker, Professor Roger Blanford, the Luke Blossom Professor at the Stanford University and Stanford Linear Accelerator Center. Professor Blanford is one of the most renowned astrophysicists of the current era. He has made seminal contributions to the extremely broad spectrum of astrophysical problems, from the understanding of astrophysical black holes and their relativistic jets, and also to the modeling and interpretation of gravitational lensing and astrophysical particles and gravitational waves. For his foundational contribution to astronomy and astrophysics, Professor Blanford has been elected as a Legacy Fellow of the American Astronomical Society, and he has received many prestigious awards, including the Humboldt Prize, the Crawford Prize, and the Shaw Prize in Astronomy in 2020. So today, Professor Blanford will share with us about his exciting research on extreme astrophysics. So please join me in welcoming Professor Blanford. Roger, the stage is yours.
Thank you very much, Jane. Can you hear me?
Yes, we can.
You can. Excellent. Okay. Well, it's a great pleasure on my part to be able to participate in this Hong Kong Laureates Forum, and a double pleasure to be introduced by my colleague, Professor Jane Dye, of whom I'm immensely proud. So thank you very much, Jane, and thank you everyone for your kind invitation. I prepared a short presentation which I'd like to give on what I call extreme astrophysics. And I've picked here essentially 5 areas that I'm just going to go through very fast. And what they have in common is that they push the extreme into territory that you could never hope to reproduce on Earth, and also that they are open puzzles in many regards. It's not the sort of physics or astrophysics that you can look up in a textbook and remember for an exam. It's ones where there are active debates and discussions going on as to what lies behind these extreme astrophysics in these 5 cases. And I think a third characteristic is that they're all ones where I at least sense that we will know in not so distant future which of these many competing ideas we have around at the moment are actually correct. And I'm obviously going to shade this presentation towards what I think is going on, in the confident expectation that I will be proven wrong, perhaps by one of you. And so if one of you has a good, better explanation for what I'm describing, then please bring it up in one of the question answer sessions we're going to have, one behind each of these 5 topics. So just my first slide is to give this a bit of context. And this is sometimes called now multi-messenger or multi-wavelength astronomy. And can you see my cursor?
Yes, we can.
You can see the cursor, excellent. So a normal way that astronomers are represented is looking with their eyes through a big telescope out into the universe, and they'd be looking in the visible part of the electromagnetic spectrum. And as you will all know, high school students all the way to postdoctoral scholars, that this represents about 1 octave in frequency or wavelength. And if we think about the total electromagnetic spectrum as a series of grand pianos, there is sort of roughly 1/70th, if you like, of the total spectrum that's out there, and most of it is accessible to modern telescopes. So it's not surprising we're discovering a lot of strange and wonderful things when we look at the universe. But that is not all. In addition to the electromagnetic spectrum that go all the way from the radio waves at the lowest frequencies to the gamma rays at the highest frequencies, we have cosmic rays, which are seen as particles which go up to even higher energies than the gamma rays, and we have neutrinos now, which are observed increasing frequency, and then finally at the very lowest frequencies, a new development over the past 6 or 7 years is gravitational radiation. So we're seeing gravitational waves at the very lowest frequencies, and all of these waves, these 140 octaves or so, are able to teach us about the universe at large. Now, a common unit that is used for expressing the energies, if you like, of the photons or of the cosmic rays is a so-called electron volt, which is about the energy of an infrared photon, and that would be about 10 to the 19 joules. The highest energy cosmic rays in the SI system are called 1 zeta electron volt. That's about 100 joules. That's a well-hit tennis ball, for example. And the lowest energies associated gravitational radiation would be a zepto electron volt, which is 10 to the minus 40 joules. So there's a lot of energy to play with there, and I'm going to be looking at the extremes, if you like. So there's 140 octaves to explore, and one day maybe we'll add another messenger, which will be dark matter. So let me now give my list of extreme topics. The first one is I'm going to talk about cosmic rays, and those go up to energies about 1/10 of the right-hand side of that last energy scale, about 10 to the 20 electron volts. So if we look at the highest energy cosmic rays that are seen, not the lowest energy ones, which have energies about 9 orders of magnitude smaller, about 11 orders of magnitude smaller. So if we look at the highest energy cosmic rays, then these are observed as so-called air showers, and when a cosmic ray hits our atmosphere, it makes maybe 1 billion particles which come down to the ground, which can be seen either directly or through the light that they create. And the observatories are in special places on the planet. This is the one on the right-hand side, which you can see here, is in Argentina, and it's a beautiful place. I've been there, and they measure the energies and directions of these cosmic rays. Now, we know quite a lot about them. These are elementary particles that have energies of a well-hit tennis ball. We've learned through astrophysical arguments that they have to come from fairly close by in a cosmological sense, the very high energies particles. And although the regular cosmic rays come within our galaxy, these we now know come from outside our galaxy, and the best sources that we have for these cosmic rays are black holes and possibly giant shock fronts. And so shock waves that are made in the space between the galaxies, and these are the best candidates for these giant for these very energetic cosmic rays. Now, if you think about it, when I said that the energies of these particles was about 10 to the 20 of the electron volts, that means if we had something like a proton, and some of them may well be protons, then we would have to give it a potential difference of 10 to the 21 volts to give a factor of 10 leeway, if you like, 10 to the 20 minimum, but 10 to the 21 in practice. And so we need a cosmic source that can make 10 to the 21 volts, not the 1 volt of a flashlight battery, but 10 to the 21 volts. This is pretty impressive. Now, how are they made? Well, they're made by electric fields, but also alongside these electric fields become magnetic fields, and the magnetic fields scatter the cosmic rays, just like the atmosphere will scatter optical photons when we look at stars through it. One way of making these cosmic rays, which we know happens in our solar system, and we know happens around supernova remnants, and here's a picture of a supernova remnant. This is the remnant of a giant exploding supernova. is it's preceded by a giant shock wave, and basically what happens is cosmic rays rattle backwards and forwards across this shock front, gaining energy by bouncing off the approaching flows on either side of the shock front, and ultimately they can be given a small number can be given a very large energy. And we see this happening rather clearly within our galaxy around supernova remnants. We also see it in a shock front. We also suspect it's happening around our galaxy, in a giant shock front that our galaxy makes, and in the largest intergalactic shocks that surround clusters of galaxies, that some of us suspect is the source of the very highest energy cosmic rays. And that's the idea that I personally favor the most. But it's also quite possible that instead of getting the energy in lots of small changes that keep on adding up, you can have one giant black hole in an active, or perhaps in another type of active galaxy in the centers of other galaxies. And there's a lot of observations going on to try and distinguish. And as I say, I think we're going to learn more about them over the next few years. So at this point, with this slide and this very brief introduction, I'd like to allow Professor Dai to bring a couple of questions up.
Okay, thank you, Roger. I'm sure the audience here, and especially the students, might have some questions to ask Professor Blanford already. So if you have a question, please raise your hand.
Please feel free to ask questions. If you have any questions, please raise your hand. And if we also have some questions from our online audience, we'll wait for some questions from our online audience as well.
Okay, there's a question
Yep,
here.
we have a question from here.
Good evening, Professor Blanford. It is an honor to be here speaking with you. And I have a question regarding the energy gained from the cosmic waves oscillation between the ring of the shock front. So, as we all know that energy cannot be created nor destroyed, only transformed. So I want to know where all these energy eventually dissipates to. Thank you very much.
Okay, a lovely question. Indeed, energy is the key to follow the energy. That's what one should do. And what happens in this case is that the energy derives from the kinetic energy of the gas on either side of the shock front. And so you take energy out of the kinetic energy of the gas and you give it to the cosmic rays. So we balanced the books. Excellent question.
Thank you very much, Professor Blanford. I think because of the time, maybe we should move on to the next topic.
Move on to the second slide. Okay, the second messenger are the neutrinos. And where do they come from? Now, unlike the cosmic rays, we can see these are weakly interacting, and we can see them right across the universe. And here we have many suggestions that have been made for the sources of the neutrinos. And here I'm talking about the neutrinos that have energies of about 10 to the 15 electron volts. If you remember the first slide I showed you, those have energies about 10 to the 15 electron volts. That's about 1 million times the rest mass energy of a proton. Now, the sources that have been suggested have been, again, black holes and the jets associated with them, active galaxies, special types of supernova explosion, objects called gamma ray bursts, these are just names, and then especially neutron stars and and I'd say a little bit more about those, and magnetars. So let me just introduce at this point a neutron star. And a neutron star is essentially like a giant nucleus, And as we see down here, it has 10 to the 57 or so nucleons in it. So it's like really giant nucleus. It's compressed at the density of a nucleus, and it is about 10 kilometers in radius, so size of Hong Kong maybe. And then it can have magnetic fields as high as 10 to the 11, 100 billion Tesla in SI units. You can have enormous magnetic fields there, taking it well into regimes beyond the laboratory. And these are one of the candidates for making these neutrinos. Another one might be the tidal disruption event. This is the speciality of Professor Dai, and again, these have been invoked for this process. If we think about making a jet, these are the jets that are associated, that are seen, associated with giant black holes in the nuclei of galaxies. They too have been implicated in making these neutrinos. So I've said, where do they come from? And we've got a whole lot of options here, but there are observations being made by facilities like this one at the South Pole called IceCube, and they're homing in on sources. This last week was a tentative announcement of one possible source of neutrinos. How are they made? Well, this is just basic physics. You have cosmic rays that came up on the first slide, and they hit stationary protons or photons, and then there's a reaction between the two, and that makes neutrinos. So that's an introduction to this extreme petaelectron volt, million times the rest mass energy of a proton neutrinos, and the story so far. Questions?
Now we welcome questions from both our online and our in-person audience. If you have any questions, please raise your hand and our staff will pass you a microphone. If there are any questions from our online audience, please let us know, okay? Do we have any questions? All right, then I'll pass the time to Dr. Dai again.
Okay, Professor Blanford, I would like to take my privilege as the moderator and ask you one question here. As you know, there has been a lot of debate on what is responsible for the neutrinos at the very high energy end as detected by IceCube, and I would like to know your opinion and thinking on this.
I think it is a very exciting time. I think that there are sources that have been claimed, one jet like this one here, and another type of active galaxy, another type of active galaxy, which is the one that was announced this past week. These are not completely compelling in my view. I think the detection of the neutrinos is quite compelling. The association with sources, I think, in my view, it's still premature, but the fact that they're able to start making these associations is very exciting progress. There is a bit of a problem. If you can see across the universe, then you should have a very large background from unresolved distant sources, and so picking out local sources close by requires quite a bit of luck, but that could be the way the world is.
Okay, thank you very much, Professor
Thank you for the
Blanford.
question.
Yes, please.
Shall I now move on to the extreme gamma rays?
Yes, please.
So here's the extreme gamma rays, and they are now pushing up into the same energy as the neutrinos had, and that is up towards a petaelectron volt. And one of the main sources of the information about gamma rays now is a lovely facility which again I visited called LASSO in Western Sichuan, and you should all be very proud of that. This is a facility that is delivering discoveries on a regular basis, and it's still being built, so there's a lot more to come from that. So where do these high energy gamma rays come from? They probably, again, I've talked about the jets associated with big black holes. They're blamed for a lot of this, and the reason why is because they've got large voltages associated with them. Supernova remnants are also implicated in our galaxy. Sorry, let me go back. Supernova remnants and been recent discoveries. Some of these have involved LASSO and some other facilities. of sources within our galaxy that may also make these very high gamma rays, and that means they've also got to be able to accelerate very high energy cosmic rays, which is a great mystery. And then there are binary stars like this one that has the enigmatic name SS433 that makes jets on a much smaller scale than the ones associated with galaxies seen over here. And again, this has been implicated. This is also making very high energy gamma rays. So we're starting to observe the sources, identify them, and figure out what's going on in them. Now, if we think about the ways that they may make high energy photons, the principal ways are firstly using relativistic electrons, not protons this time, but electrons, and scattering off photons. And that's probably the favorite mechanism. But also we can make gamma rays from cosmic rays interacting with gas. And then the final way of doing this is to have relativistic electrons being spiraling in a magnetic field, making a type of radiation called synchrotron radiation, and in its extreme expression, this can give you gamma rays of these very, very high energies. And so the research is underway to try and distinguish these sources and the mechanisms that work in them. Next question.
Yes, we welcome the questions from the audience.
We have a question over there. Could you please stand up and ask the question so that we can all look at you? Thank you.
Hi again, Professor Blanford. It's me again. So I have a question regarding the relativistic electron spiraling in magnetic fields. I'm a little confused about that part. Can you please explain a little bit more about that? Thank you.
Okay, this is called synchrotron radiation, and we can see it in the cosmos, but we can also make it in synchrotrons in the laboratory. And basically, a simple-minded way to think about this is that this electron carries an electric field with it, and as we swirl it around in a circle, in a spiral, then it swishes the electromagnetic field around, and that electromagnetic field makes an electromagnetic wave, which you can observe in this case as a whole bunch of photons. And we have understood for a very long period of time how to calculate all of that using the formulae from Maxwell's equations and quantum electrodynamics. So it's very well understood physics, and the electrons do spiral in magnetic fields all throughout the universe, and that's a major mechanism for making radio waves through gamma rays. Thank you for the question.
Thank you very much. Is there any
So I'll now move on to the... Oh, sorry. Yep. Any more questions?
Roger, you can continue. Thanks.
Okay, so I'll now go on to gravitational waves. And here, you will know that in 2016, we've been detecting directly gamma rays using instruments like LIGO, and now a European instrument called Virgo, and there's a Chinese version under development. And we also have seen them for a lot longer using pairs of neutron stars spiraling about each other, and we've seen the indirect effects of the emission of gravitational radiation. So it's a very real physics phenomenon. And what has been detected so far are the highest frequency gamma rays, which comes basically from mergers of neutron stars and especially many black holes merging together. And this is a pretty secure identification. In the future, and this is the great excitement of this business, space-based interferometers will take us to lower frequencies. Even lower frequencies are being seen by measuring gamma rays using pulsar timing. The lowest frequencies of all come from observations of the cosmic microwave background. So this is all very much in the future, but it's a very rapidly growing field. So I've said, how are they made? Well, they are made, the ones that we observed directly are made mostly by merging black holes. They've been the most popular source, but they also come from neutron stars. And I said jets are everywhere. These merging neutron stars also make jets. And if you say, how well do we understand the theory of this using Einstein's general relativity, here's a fit to the data of the behavior of binary neutron stars emitting gravitational waves. So it's been great for physics, great for astrophysics, and great for experimental science. Questions?
Okay, Professor Blanford, here I would like to read a question from the audience online. So they have asked that, the observation of gravitational wave is only made possible decades after Einstein's general theory of relativity, predicting the existence by some genius engineering feat in the form of LIGO. So which type of equipment do you think that we will need to explore next to the next physics in gravitational theory?
In terms of gravitational waves, there's an attempt to use a version of LIGO using so-called interferometry going into space, being launched in space, and that will look at lower frequencies. And then the thing that is underway at the moment, and it is on the verge of detecting a background, it hasn't quite got there yet, is what's called a pulsar timing array. This is looking at lots of pulsars, which are spinning magnetized neutron stars that have frequencies about 100 hertz or so, and you use those as clocks. And by measuring the arrival time of those pulses, you can see intervening gravitational waves, and that's a technique that is almost delivering detections. Not quite there yet, almost there yet. And as I said, microwave background observations, will access the lowest frequency gravitational waves. So there's a lot going on, and all of this is experimental physics applied to astronomical sources at the very highest level. This is extremely hard, takes decades to bring to fruition, and it's very exciting.
Thank you very much.
Let me turn to my final extreme astrophysics example, and this is something that again is very much in the news right now. These are called fast radio bursts. They were first discovered about 13 years ago, and they're little bursts of radiation. They happen about 1 per minute, and what's extreme about them is the effective temperature of these very bright bursts, if we can ascribe a temperature to them, is about 10 to the 35 degrees Kelvin. That's very, very hot, but it's saying it's a macroscopic phenomenon, like a tsunami, that also has a temperature of about 10 to the 35 degrees. And we see these across the universe. We've learned a lot about them over the last 5 or 6 years. And I mentioned the magnetars, which are these highly magnetized young neutron stars with 10 to the 11 Tesla fields. They are now, for reasons of observation and theory, are the favorite origins for most of these fast radio bursts. And so what we think is going on is that there's a starquake, like an earthquake, shown here in the bottom left-hand corner, on the surface of the neutron star, which shakes magnetic field around like it does on the sun. So here's Harrison Ford with his whip. That magnetic field sends magnetic shock fronts out, if you like, which make these giant tsunamis, which become electrical displays of lightning. And so this gives us radio emission at the end of the day, which can be seen by giant telescopes, like especially the Fast Radio Telescope in southwestern China, which again is another facility to be immensely proud of. And they produce the radio bursts like this. We're learning a lot about these, and as I say, there's hundreds of explanations out there. The best bet at the moment looks like magnetic flares, but there could be more than one explanation. I hope so. It's and they're not only are they fascinating physics in their own right, they're also wonderful tools for doing astrophysics and cosmology. So let me just finish at this point with a summary slide, which I'll keep up, ask for questions about the fast radio bursts and any other topics that have come up. And I think that's my time is up now.
Thank you very much, Professor Blanford. So we will have the final Q&A session, and we can accommodate 1 to 2 questions.
Do we have any questions from our live audience? If you do, please raise your hand and let us know. We have a question over there. Again, please stand up so that we can all see you. Thank you.
Hi, Professor Blanford. So I have yet another question on fast radio bursts. So what are the differences between fast radio bursts and bursts that are emitted by pulsars? Thank you.
A very good question, clearly based on some understanding of what goes on. There are pulsars, which are just for the audience, are spinning magnetized neutron stars, and one of the most famous of this is the Crab pulsar, the pulsar with a 33 millisecond period. Now it's 34 milliseconds. When I was a child, it was 33 milliseconds. Now it's 34 milliseconds, and this creates very occasionally very high brightness radio pulses. And many astronomers have said the much brighter fast radio bursts are the same phenomenon going on as happens in the pulsars. Now, the pulsar in the Crab Nebula has only a 10 to the 12th Gauss field. The magnetars are 10 to the 15 Gauss field. I personally, I have rather specific ideas of what's happening in these sources, and in my version of what's going on, which is one of many, there is a large similarity between the physics that makes the pulses in pulsars and the occasional flares in gamma ray bursts. But to go into the details would be too long for this session. But that is an association that's partly won by observation, but also one on the basis of rather similar physics processes, but scaled up as you go from the radio pulsar to the fast radio burst.
Thank you very much, Roger. And any more questions? Okay, so I think due to the time constraint, let's conclude Roger's talk. And thank you again, Professor Blanford. It has been a great pleasure to see you, and we thank you for bringing this interactive section with the students. Okay, so let's move on to the next speaker. Okay, our next speaker is Professor Ming-Chung Chu, the Chaoming Li, Professor of Physics from the Chinese University of Hong Kong. Professor Chu has done many important work in the broad area of astrophysics, cosmology, and particle physics. Furthermore, he has been the PI of the Hong Kong team of the Daya Bay reactor neutrino experiment, which had made groundbreaking discoveries on neutrinos that helps explain the evolution of the universe. Professor Chu has received many awards for his research achievements, and including the Breakthrough Prize in Fundamental Physics that he has received together with the Daya Bay collaboration. So without further ado, please join me in welcoming Professor Chu for his talk on supernovae. Please.
Thank you, Jane. Good morning, and it's really my honor to be here. Before I start my talk, I'd like to make two personal notes. So the first one is to thank Professor Roger Blanford. I took a course in general relativity taught by him many years ago, before most of you were born. And yeah, I still remember it. It was tough, but I learned a lot. Second personal note, I see many young faces today. I'm particularly happy about it. Yeah. Young and energetic. I got into physics because I was interested in astronomy. I did my secondary schools in Hong Kong, and I was one of the organizers of the astronomy club. I really loved looking at the stars and so on, setting up telescopes, reading books about astronomy, and I got really fascinated by all these special celestial objects like black holes, Big Bang, and things like that. I'm still a diehard fan of astronomy, astrophysics, and I'm very lucky that I can actually do research in these areas. And I can tell you, over the past 40 years or so, astronomy actually got even more exciting. There's so much more new phenomena. You've just heard many of them in Professor Blanford's talk. And I'm sure in the coming years, it will get even much more exciting. So I pick a topic that sort of bridges between Professor Blanford's talk and Professor Look's talk on neutrino. So I pick a topic that will serve as an example what may come in the next 10 years or so. I think we'll understand much more about our universe. So traditionally in astronomy, astrophysics areas, but we can hope to understand much more by using particles as probes. Okay, so let me go on. I'll talk about the heart of a dying star. So I did not mean for this to be a poetic title. I mean for it to be a literal title. Okay, I think many of you know that stars would die, our sun would die. And many stars would die spectacularly in huge explosions. Okay? Professor Blanford already mentioned this Crab Nebula. And we believe that this was made by a star that died about 1,000 years ago. Today, we have a standard picture how stars die. So if you take a standard course in astronomy, this is probably a picture that you would know, you would see. It's too complicated. Depending on the mass of the star, it would die differently. But the most massive stars, say 10 solar mass or so, they would eventually end up being a core collapse supernova. I'll explain a little bit more about this. Okay? And that's the spectacular explosion that produced the Crab Nebula and other very interesting looking nebulae. Okay, so here's an example of a supernova in a galaxy very far away. Now, when that star exploded, you can see that it's actually brighter than the entire galaxy, about 100 billions of stars. One star die is brighter than 100 billion stars. The fireballs it made would have temperature around 10 to 11 degrees. So this is really interesting phenomenon producing all these nebulae that we can study. In each galaxy, such as our Milky Way, on average, you can expect to have one such supernova about 50 years. Okay? I haven't watched one myself. I really hope I can see that one day. Some of the brightest supernovae, according to history, for example, this one, astronomers recorded that they could see the star. They call it a new star, right? Even during daytime. Right? So imagine looking out there, you see a bright star there. Okay? That's how spectacular a supernova can get. Okay, let me go a little bit fast. Now, in the coming 10 years or so, I'm sure we'll have a lot more understanding about how stars die. That is because we now have many new tools to study them, including neutrinos, with many neutrino detectors. You can think of them as neutrino telescopes, gravitational telescopes, and traditional telescopes. So these tools allow us to look into the supernova in different ranges. In particular, neutrinos and gravitational wave will allow us to look all the way to the core of the supernova. Light cannot do that. We can only see the surface of the fireball. We don't know what's going on inside. But these new tools, neutrinos and gravitational wave, will allow us to do so. So, just a very brief picture of how a core collapse supernova would happen. Okay? So, a massive stars will evolve, there will nuclear fusion in the core, until it gets to an iron core. You cannot extract any more energy by nuclear reactions with iron. So an iron core would not generate any more energy. Gravity would win. So this core of the star would collapse under its gravity. That's the first stage. It's really an amazing collapse. We're talking about collapse of something like one solar mass object, the core of this massive star. Okay? Within a fraction of a second, down to several hundred of kilometers. Within a fraction of a second. Reaching such a high density that the electrons and protons will be squeezed together to become neutrons and emitting neutrinos. These neutrinos will come out in large quantity. But once you make the core into a neutron core, then the repulsive force among the neutrons would resist further collapse, set up a shock wave, and explode the envelope. That is the sort of standard scenario we have for now. We're not sure this is correct, because nobody could look into the core of such stars yet. But this is sort of the picture we have today. Right? And this is a simulation, not done by me, done by some scientists in Germany, of how a collapsing core may look like. Okay? So you see the hearts there. Again, that's not deliberate. Okay? But it's a highly complicated process. And it takes a lot of work in doing all this numerical computation. Now, again, if we look at a supernova from afar, from Earth, let's say, using traditional telescope, this is all you can see. Wow, really bright. I see a bright spot in the sky, but this is all you can see. What's happening inside? What's happening at this core? That's the question. Neutrinos from supernova have been observed already in the 1987. 1987, there was a star that died and exploded, and 3 of the neutrino detectors at that time picked up a burst of neutrinos within a short time. So these are believed to be coming from the core of this dying star. Now, those data were already very, very interesting, but they're not of high quality yet by today's standard. So we still could not decode all these neutrino signals to really test how the core collapsed. Neutrinos are nice because they interact so weakly that they can penetrate through the entire star. So sometimes you call them ghost particles. Professor Lok will tell you much more about neutrinos. Now, by being ghosts, that means it's very difficult to detect them, but there are many of them. Right? Actually, if you consider yourself, okay, so if I stick my hand up, every second, trillions of neutrinos pass through. Most of them from the sun, from the core of the sun. Day and night. So at night, they go up. The sun is down there. The neutrinos penetrate all through the sun, through the earth. Trillions of them pass through your body every second. They don't do anything to you. That's why we call them ghost particles. But that's nice because they come out all the way from the core of the star where they were made. And now we can actually detect such signals from the Earth. And in fact, the neutrinos carry more than 99% of the energy of such a supernova. The bright fireball, the lights you can see, is a negligible fraction of the energy. Neutrinos carry most of the energy. So if you really want to understand supernovae, you better detect the neutrinos. Okay, so another new tool we have, and Professor Blanford has already mentioned it, is gravitational waves. I believe that most of you have heard about gravitational waves already. But just a very quick introduction. In general relativity, space and time are deformable. You curve them, so it's hard to imagine, right? Well, think about time, right? We probably intuitively think that 1 second is 1 second everywhere. Same here on Earth, same on the moon, same near the black hole, same everywhere. It's an absolute clock. Not correct. Einstein tells us that time is relative, space is relative. Time could even be not uniform, particularly in the gravitational field. So the clock near the surface of Earth and up there in space, they run at different rates. That's how we can imagine time would be deformed. Similarly for space. And if so you can visualize this deformation of space and time, such as in this animation. A deformable medium would naturally support waves. You just put some objects, disturb this deformable medium, then you can make waves. That's gravitational waves. So these are waves of space and time that we can detect today. So this is an example of the gravitational waves generated by binary black holes. 2 black holes orbiting each other, merging, and this process would generate huge bursts of gravitational waves. And these have been detected. And again, I'm getting old. So I must tell you that when I went to Caltech as an undergraduate student, and that's where I took the general relativity course taught by Professor Blanford. When I got there, that same year, I went to visit the LIGO prototype. So it was on campus, 4-meter arm's length. That was in the early 80s. So they only measured gravitational waves less than 10 years ago. So imagine how hard, we're talking about 30, 40 years of hard work before they really achieved the goal. But now the field is really exploding. There's so much new things they can do, including, hopefully not too far in the future, they could detect the gravitational waves generated by these exploding stars, by the collapsing core and the explosion of the supernovae. Now, just as an example, let me tell you one calculation we did to make some prediction to see what they could see in gravitational waves and neutrinos if there's a core collapse supernova somewhere nearby within Milky Way, let's say. Now, in particle physics, we know that protons and neutrons are not elementary particles. They're made of quarks and gluons. So there are these tiny particles inside the protons and neutrons. Nobody has seen a free quark yet. So for a long time, physicists try to understand how we may liberate the quarks and gluons. So one way to do it is to heat matter up. If you heat them up to high enough temperature, we're talking about 10 to the 12 K, then the quarks would be liberated, forming a new form of matter. Sometimes we call it quark matter. Okay? So you either go up in temperature, you go up in density, you can transform matter into a new phase, quark matter phase. This has been done in the lab, in collider experiments and so on. So we wonder, and not just us, many astrophysicists wonder whether during this core collapse, the core can get so hot and so dense that it transforms itself into a quark star, a little star made of quarks and gluons. And if so, can we know about it? Okay, so let's make this long story short. We did a simulation using some supercomputer, general relativistic hydrodynamic simulations, comparing with and without this transformation into quark matter. How would these collapse supernovae be different, and what signals they would give us? Okay, so this is a simulation done by my ex-PhD student, Swai. Okay. Now, so to make the story short, we predicted that if a quark core is formed, there will be two bursts of neutrinos separated by about 0.4 seconds or so, right? Fraction of a second. So modern day neutrino detectors will have high time resolution. They could really know. You see a first burst, initial collapse. The core gets so hot, so dense, it transforms into quark core, a quark star. Another burst of neutrinos, almost as strong as the first burst. That would be a very good signal. Furthermore, we look at the gravitational wave signal. Okay, so a star initially slowly rotating, and then when it collapses, it rotates very fast. And if you have a quark core, then you will again see a second burst of gravitational waves. And in this case, actually even stronger than the first gravitational wave burst. So again, two bursts, very strong gravitational wave signal with some waveform that we can calculate, and hopefully one day they will detect it, and then we can do some matching, and then we know much more about the core. Okay, so let me skip this and make my summary. Okay. Now again, this was just one example. We might be wrong. Maybe there's no quark core. We don't know. But as an example, I hope to impress upon you that there could be many, many new things, exciting things coming up. We can understand supernovae, we can understand many celestial objects much better in the coming years. Okay? So the particular example I show you is that massive stars would die as core collapse supernovae. Would explode, will be very bright. It's very important for astrophysics and cosmology. But we don't know much yet, particularly what happened at the core. So I told you that the core collapse will produce a huge burst of neutrinos, carrying away most of the energy. And such neutrinos have already been detected. Now it's time to wait for the next one. And if you see something like two neutrino bursts separated by a fraction of a second, it's telling us that something's happening at the core, maybe a transition into a quark core. At the same time, we predict two bursts of gravitational waves, the second one even stronger, even faster. So if we see that, that's a very strong suggestion that there's some transformation into quark matter, so we can study both particle physics and astrophysics at the same time using such observations. think I'm right on time here. Professor Blanford has already told you about this, so I will skip this. This is just news about new detection of neutrinos from probably a black hole was announced only last week. So it's really an exciting era that we can expect much more exciting news. Okay, I'll stop here. Thank you. Okay.
Thank you very much, Professor Chu, for this very exciting talk. Okay, now let's welcome the audience for questions. Please raise your hand if you have any question.
Do we have any questions from our live audience? Please raise your hands if you do. And also, do we have any question from our online audience?
Okay, I'll start with this question, which I really like. So, Professor Chu, you have been an astronomy enthusiastic since you were very young, as you have told us. While many youngsters may be stargazers, very few of them end up pursuing astronomy as a career. So what do you think that is? Why do you think that is the case?
Yeah, good question. I always wonder about that too. I always see young students really interested in not just astronomy, but fundamental science. And I really felt very good. But as they grow up, they probably switch into something else, okay? Finance, medicine, so on. No problem, I have no problem with that. But I always hope that we can see more scientists from Hong Kong. Now, as far as I can tell, Hong Kong students are among the smartest students in the world. They can do great things. When I was a high school student, all the big news about science came from foreign countries. I think that have been changed, okay? You see great scientists here, there, okay? They have done great works, world-class work. We can do it. Hong Kong people can really do it. And that we're talking about long-term impacts now. You make your discovery, that's really for the long term. That's contributions to humankind, to civilization. So I really hope that Hong Kong people would not be so short-sighted and contribute to some long-term work, making long-term impact. But back to your question, I believe that the society, probably your family, they would discourage you into going into pure science, fundamental science. I understand those. I understand the concern. At the same time, I encourage you, if you have the interest, if you have the desire, if you have the drive to make some really fundamental discoveries, science is exciting, and this is actually the golden time, exciting time to go into science.
Thank you very much. Is there any more question from the audience? Okay, so let me ask you another question from... Oh, yeah, okay, sorry.
So, excuse me, like you had said that we have those cool observers, like telescopes, that we can like observe the collision of stars or the stars dying. So I'm curious, what will happen, or did we able to observe like two black holes colliding with each other? What will happen like inside the black hole? Thank you.
Yeah, nice question. Okay, so yeah, in fact, there have been many binary black hole merging into each other, and they form a bigger black holes usually. Okay, so we have been observing those using gravitational waves. Okay, so LIGO has been doing all those. So all we can do at this point is to make simulations. Okay, so you do calculation using general relativity, simulate what will happen, predicts the gravitational waveform. Now, LIGO would measure those waveform, and you do a matching. So when you match the waveform, you know roughly what goes on. Okay, what were the initial masses of the black holes, and finally, after they merge, they form a bigger black hole. They would vibrate a bit and then die down. So we can know all these processes. However, we cannot look inside a black hole yet. We cannot do that anyway. So the gravitational waves we can detect, they all come from outside the black hole. That's all we can do at this point. Too bad. Einstein said that we cannot look inside a black hole. Okay? Maybe Einstein is wrong, I don't know. But still, it's very good already that we can see what happened from outside a black hole. Okay?
Thank you very much. One more question.
Hi, Professor Chu. So I have a question regarding the quark matter and the quark collapse. So you mentioned that if a quark core is formed, there will be two bursts of neutrinos separated by about 0.4 seconds, as well as two bursts of gravitational wave. The second one is stronger than the first. So is it because there is a second collapse of the core? Thank you.
Right. Good question, yeah. So the initial collapse would make a very hot and dense, still so-called hadronic matter, still neutron mostly. Okay? But then after the phase transition, it will collapse into a quark star. So there's two collapses, basically.
Thank you very much. So due to the time constraint, let's thank Professor Chu again for this nice talk. And thanks to the audience for the questions. Okay, so let me introduce our next and last speaker of today, Professor Ken-Bill Luke, the IAS Paul C.W. Chu Professor and Chair Professor of Physics at the Hong Kong University of Science and Technology. Professor Luke has made seminal discoveries in particle physics and cosmology. And in particular, he is the co-leader of the Diabase reactor neutrino experiment and has received the Breakthrough Prize in Fundamental Physics together with the team. Furthermore, together with his collaborator, Professor Luke was awarded the 2014 WKH Panofsky Prize in Experimental Particle Physics from the American Physical Society for his leadership of the Diabase experiment. So please join me in welcoming Professor Luke to the stage for his talk on neutrino oscillations. Professor Luke.
Well, thank you for the nice introduction. And also, I would like to thank the organizer for inviting me here to share some of my research with you. Since we are running out of time, so I will not say too much, but I just want to also tell you a story. Certainly, when I was young, I didn't have any cell phone, or video games like that. So usually I built, models, airplanes, and even telescope, just to keep myself busy. And I would say probably because of this kind of games. So gradually, I realized I like science and also engineering. And then, like many of you know, when I was a student of University of Hong Kong, I thought, great, I can become a theorist. However, when I study for my PhD in the US, then I realized actually my love is really in building things. So as a result, I decided to become an experimentalist. And I would say it's very sad that not many students from Asia, in particular from Hong Kong and China, do not like experimental physics. And I think it really hurts a lot in advancing field, because science, after all, depends on observation. And it doesn't matter how beautiful a theory is, without experimental confirmation, it's just a dream. Rather than spending time talking about all this side story, so let me now get to my talk. because I am an experimental particle physicist, so usually what I do is to look for new particles or new fundamental forces. And once we find say new particles or a new force, then usually we'll study the properties of say these new entries. Now, Professor Blanford and also Professor Chu have talked about the neutrinos a little bit. So therefore, I will just tell you right now, as far as the experimental, or I should say particle physicists that are concerned, we know the basic building blocks of visible matter are made up of quarks and also the leptons. And altogether, we have three generations of quarks and leptons. And you can see in each generation, we have a neutrino. So as a result, we have three kinds of neutrinos in nature. So we call the electron neutrino, the muon, and the tau neutrino. Now, what we have learned about the neutrinos that can be summarized in this. They have a very, very small mass. For instance, if you look at say this cartoon picture of the atom, then you'll notice the electron and the quark, which is inside the proton, and then the neutron, they have extremely small mass. As a matter of fact, right now we still have no idea how large all these elementary particles are. And neutrinos, essentially behave in a similar way. Very, very tiny. And furthermore, because they do not carry any electric charge, so as a result, they only participate in weak interaction. So that's the reason why Professor Chu said that neutrinos, can essentially escape, from, say the supernovae. Now, because of say this, the interesting properties of the neutrinos, they have say very little interaction with ordinary matter. So as a result, it's an ideal probe for us to study the sun. In particular, when the sun generates heat and light through nuclear fusion at the center of the sun, neutrinos are produced. So one question in the 60s was to decide how we can detect neutrinos from the sun so that we can then study the inner structure of the sun, and subsequently how we get our energy indirectly. Now, Professor Davis and his collaborator built a detector about I'm trying to convert them into SI unit because this mine is quite deep. It's about 50 feet from the surface. So that will be on the order about the 3 kilometers or so, if I get it right. All right. So by detecting or counting the number of solar neutrinos for about 20 years or so, you can see the result is very different from the prediction. So therefore, the immediate question we have to ask is whether we don't understand the sun, or say something wrong that we overlook about the neutrino. So for a while, this was called a solar neutrino problem. Now then, around the end of this experiment, then in Japan, a gigantic 50 kiloton water detector was built. Inside this Kamiokande mine, this detector is called the Super Kamiokande. Now, when the physicists use this detector to count the number of muon neutrino produced by cosmic ray hitting our atmosphere, then they realize that for the neutrinos coming from the south pole through the detector, corresponding to, let's say, this quantity cosine theta equals to -1. Then you can see, okay, that the number of mu1 neutrinos detected by the detector is far less than the expectation. So this is, okay, certainly really shocking and also very interesting. So then in this case, okay, we have to ask whether, okay, say we do not understand how cosmic ray interacts with air molecules in the atmosphere, or again, okay, something is wrong with, say, the neutrino. Now, in the particle physics, okay, community, we suspect the problem is related to, okay, the neutrino. The way, okay, we explain, okay, say the result will be something like this. Now imagine, say, in the beginning, we have a certain number of, okay, say, actors wearing, okay, say, this kind of, okay, face mask. And as you know, okay, this is very popular, okay, in Sichuan. And the actors, okay, can instantaneously, change, okay, say, the mask to a different one. So therefore now, imagine, okay, in the beginning, if we have, say, a certain number of masks like this, but a few of them got switched to, okay, say, either this one or this type, then naturally, then the number of, okay, say, the actor with this mask will be less. So therefore, in this case, okay, that would explain, why, okay, when we detect, okay, say, a particular type of neutrinos in the experiment, then we will see less. Right? Now, certainly, this is, okay, the very intriguing idea. So it's very important for us to, okay, check it experimentally. Now, one of the very important things, okay, as a consequence of, okay, say say this, okay, the identity-changing game is, okay, if we see, okay, say this kind of, okay, behavior, then we can infer right away neutrinos, okay, have to have mass, which is, okay, totally contradicting, what we know, okay, in the standard model. Because in the standard model, we assume the neutrinos are massless. Now, in order to test, okay, say this idea, then the scientists, okay, built a kilometer of detector with, okay, heavy water, which is very deep underground in a nickel mine in Canada. Now, the advantage of using heavy water is this. Okay, this will allow us to count the number of neutrinos using this, okay, 4 kinds of reactions. And it turns out some of them will be sensitive to the electron type. Some will be sensitive to all of them. So therefore, as a result, by studying, okay, all these 4 reactions, then we can tell, how many electron type of neutrinos are produced, okay, by the sun, and also, okay, say how many of them will be the other type. And the nice thing is, okay, the experimental result came out like this. And to give you some idea, okay, the Professor Davis experiment essentially could only count, okay, say the electron type. However, now for this, okay, experiment called SNOW, using these other reactions, okay, we can also count the number of, okay, muon and the tau type. So when we add them together, you can see the total number of neutrinos coming from the sun detected by the experiment is consistent with our expectation. So therefore, this demonstrates that indeed, when the neutrinos coming from the center of the sun towards Earth, some of them, okay, change, okay, their favor. So therefore, okay, in Professor Davis' experiment, if they only focus on the electron type, then naturally they will see less than, okay, expectation. Right. Now, of course, we still have, okay, say a loophole here because, this SNOW experiment and also, okay, say the super Cam-Yokan Day experiment, all these experiments utilize neutrinos produced by nature. We have no control. So in other words, okay, you can consider this kind of, okay, say detectors as, okay, say like telescope, but for seeing, okay, neutrinos, okay, from nature. Now, in order for us to really confirm the favor changing concept is correct, then on Earth we have to really design experiments in a controlled manner so that, okay, we can tell, what's going on with the neutrinos. Now, in order, to do it, on Earth, then we have to, understand neutrino oscillation a little bit more because, this will affect how, we want to design the experiment. Now, it turns out, in order for us to understand, neutrino oscillation, we need to introduce, 6 fundamental parameters. Up to now, we cannot explain using theory. So therefore, we have to do experiments to measure the values of all these 6 quantities. So 3 of them are called the neutrino mixing angles. And then there's one complex phase related to something we call symmetry that I will say a few words towards the end of my talk. And then the last 2 are related to the mass squared difference between the neutrino states that we call 1, 2, and 3, but we do not see them in the experiment. All right. Now, using these 6 quantities, then it turns out then we can write down the probability if we start off, say, for instance, in this example, electron type of neutrinos, then ask the question, after the neutrino travel a certain distance L, how many of them will survive still as electron neutrinos. So from this, approximation, you can see, there are 2 sine square terms. One is, the, sine square times, 2 times, say a mixing angle. It turns out, if we graph, this equation, then we'll see, say a pattern like this. And the sine square 2 theta essentially give us, the amplitude of, this, say, oscillatory pattern. Whereas, say, the other term, you can see it depends on, the mass square difference here, and also inversely depending on the energy of the neutrino, and also the distance between the birthplace and the detector of the neutrino. This will give us either the frequency of the oscillation or the wavelength. So subsequently, when we design experiment, what we want to do is to come up with say a neutrino beam with a certain energy. So from this equation, then we will know, say where we want to position the detector, so that we can see, say the oscillatory pattern here. Now, using, say this idea, then we can then now look into, say experiments. So the first one I want to talk about is the one called MINO and MINO plus experiment that was done in the U.S. In this experiment, we used the Fermi accelerator to produce an intense neutrino beams, so that we can shoot the beam towards a iron mine in Minnesota. This is called the Sudan mine. Inside of the mine, we put a 5 kiloton of a detector to observe, say, the neutrino interaction. So this is a picture just to illustrate how we detect that neutrino interaction in the experiment. Now, after several years of data taking, the MINOs and MINO plus experiment observe something like this. What we are seeing now, the y-axis is the number of neutrinos detected, and the x-axis is the energy of the neutrinos that they observe. Now you can see the experimental data points is very different from the prediction. As a matter of fact, if we take the ratio, say for any given say energy, then we end up with say a pattern like this. So now this one, okay, doesn't look like, okay, say the one we saw, but at least, okay, it demonstrates that indeed some of the muon neutrinos, by the time they get to the detector, they change to okay, something else. So as a result, okay, when we okay, say compare with the prediction, then the number is less than 1. It's like that. Now, using okay, say this pattern, then we can then extract the information about the mixing angle. In this case, okay, is the mixing angle called okay, theta 2,3, and also okay, the delta m squared related to either the frequency or the wavelength, okay, given by this okay, quantity. All right. Now, so using okay, say MINO plus okay, as an example, essentially we have okay, say confirm atmospheric okay, neutrino oscillation, because okay, in atmosphere okay, most of the time we produce okay, the muon type. Now, then how about okay, say the solar neutrinos? In that case, okay, we are talking about electron neutrino. Now, in order okay, say to check this problem, then at the beginning of the millennium, we had a detector okay, called okay, the CAMLAN installed okay, in the cavern that Professor Chu talked about okay, say the Kamiokande detector, because after they discovered the neutrino from supernova explosion, then they stopped the experiment and use okay, another okay, place of okay, the mine to build okay, the super Kamiokande detector. And we utilize this okay, the empty cavern to install a new detector called CAMLAN, because instead of using water, we use okay, 1 kiloton of liquid scintillator. Because okay, when the neutrino interacts inside the detector, it will produce okay, the some light through okay, say this scintillator. So as a result, then we can study okay, the neutrino interaction. Now, in order to do this experiment, we utilize essentially all the nuclear reactors okay, in Japan. At that time, there were about okay, 55 of them. Now, after about 2 years of data collection, then we observed say a spectrum like this. Again, when we okay, say have okay, say the data points comparing with the expectation, then you find out essentially the CAMLAN observed far less antineutrinos than the expectation. So this essentially confirmed the solar neutrino problem. That is, okay, the problem is related to neutrino oscillation. And subsequently, then using okay, again the spectral information and also okay, say the number of electron antineutrino okay, disappeared, then we can determine the delta m squared okay, 1, 2. With okay, this value, and you can see this is about 50 times smaller than the other delta m squared 3, 2 okay, measured by say the other experiment using muon neutrinos. And also okay, we can measure the mixing angle okay, called okay, theta 1, 2, like that. Now also okay, in CAMLAN, because of okay, say the equation governing the oscillation at okay, say 100 kilometer location, we got say a rough measurement of okay, say the mixing angle theta 1, 3. Now, however, because the uncertainty of okay, say the measurement is very large, essentially CAMLAN could not tell whether okay, say theta 1, 3 would be less than smaller than 0 or not. So in order for us to okay, determine the values of the mixing angle theta 1, 3, then we need to build a new experiment. So in 2002, then I started to look at the location for mounting a new experiment, to measure theta 1-3. And also, this is it's also a side story. In the summer of 2003, when I came back to Hong Kong and had dinner with Professor Zhu and also a few colleagues from University of Hong Kong, and I managed to convince them that this is an experiment Hong Kong should do. However, because Hong Kong is a small place, so therefore, we convinced the colleagues in China and also from Taiwan and also from the US to join force to build a new experiment to detect the reactor antineutrino so that we can measure theta 1-3. Now, besides the diabetic experiment, actually we have two other competing experiments, one in Europe and also one in South Korea. Now, however, when we compare, let's say, the capabilities of these three experiments, diabase, certainly, emerge as, say, the winner. So this is a picture of, say, the diabase nuclear power plant, and you can see, we have two reactors here. This is called the diabase nuclear power plant. As a matter of fact, in 2003. The diabase nuclear power plant produced about 75% of say the electricity used in Hong Kong. But now we have used so much the electricity. Now the fraction is down to only about 25% or so. So therefore we need to save energy. Now besides say the diabase nuclear power plant, we also have the two other called the Ning-Ao nuclear power plant and Ning-Ao 2 nuclear power plant. Altogether, there are 6 nuclear reactors, about 50 kilometers from where we are. So this is very nice because the more reactors we have, that means the more antineutrinos it will produce. That will allow us to do the experiment better. And furthermore, because it's right by say a mountain, so therefore it's really good for us to essentially build underground experimental halls for detecting, say, the neutrinos. So this is, I think I'm missing. All right. So this is essentially how the experiment looked like. So the black line is the tunnel. Altogether, we have to dig 3 kilometer long tunnels, and then with 3 experimental halls. 2 of them are very close to the reactors, so that we can count number of antineutrinos produced by the reactors, so that we can forecast how many we should see at say the far detector. Now, unfortunately, because the figure for some reason is missing, I cannot show you what we observe. However, the bottom line is we also observe 8% of the antineutrinos coming from the 6 reactors disappear by the time they travel about 1.6 kilometer into the mountain. And as a result, then we can determine the mixing angle theta 1-3, and also say the mass square is the 3-2 using this approach. Now theta 1-3 was a very important quantity in about say 20 years ago, because if theta 1-3 was 0, then basically we cannot study neutrino oscillation anymore. Essentially, then the research of this area more or less come to an end. Now, however, because theta 1-3 now is shown not 0, so as a result, this allows us to continue to study some other properties of the neutrino oscillation. Okay. So even though the other one missing, I can show you this one. So now you can see, say the diabase oscillation pattern. You can clearly see, say the oscillatory, pattern due to the mixing angle theta 1,3, and then for say the cam length, which measure the oscillation of theta 1,2, you can see it's like that. So certainly this is very convincing that we have observed say the phenomenon. Now coming back, because of theta 1,3 is not zero, then we can now design new experiments to address the two remaining questions related to neutrino oscillation. One of them is related to what we call say the mass ordering. Recall that the mass square difference is related to say the mass of say some unseen neutrino states. Okay, now right now we have no idea whether say the mass of say the third neutrino state is the heaviest or the lightest. So there are a couple ways we can determine this say the pattern one way or the other using say the different techniques. However, one of the approach again is to use nuclear reactor. So in this case, right now as we speak, there's a team hosted by the China building a brand new detector called Juno, which is in German. This detector is huge. It has 20 kiloton of liquid scintillator to detect antineutrinos coming from two relatively new nuclear power plants in the western part of Guangdong. Now the whole idea of the Juno experiment is to try to determine the fine structure of the oscillation pattern due to the mixing angle theta 1,3. So if they can somehow determine the position of all these say tiny peaks, then essentially they can tell which one is the correct one. That is whether say M3 is the heaviest or the lightest. And this experiment should come online very soon. It might be say as soon as next year. And by the end of this decade, then this experiment, if everything works out as planned, then they should be able to tell us say which is the correct solution. So therefore, it's something for you to watch. Now, then there's also the one remaining question related to neutrino oscillation. And probably this is my only slide related to astronomy, because one of the open questions in science is why say the current universe has only matter, and we don't see say antimatter at all. So this is the say what we call say the matter and antimatter asymmetry. So the question is whether say the neutrinos can help us in understanding say say this the peculiar say the phenomenon. Now, in order say for us to say get some idea about say the say that problem, then we speculate that maybe the phase I mentioned earlier on related to neutrino oscillation may have something to do with the matter and antimatter asymmetry of the universe. Because if this say phase is 0 or pi, then basically matter and antimatter will be equal. There should be no imbalance. However, if theta the Cp is not 0 or pi, then there's a chance that this say the phase may have say some implication for us to solve the say the bigger problem. So in order for us to say find out the size of this phase, right now, okay, worldwide, there are 2 experiments being designed and also, okay, partly under construction. One is, okay, called the Dune experiment, hosted, okay, by the U.S., using the accelerator at Fermilab to produce a very intense muon neutrino beam, and then send all these neutrinos to the home state mine that Professor Davis used, but now, okay, we refurbished the cavern and make it bigger, so then, okay, we can put 4 gigantic detectors underground to see how many of the muon neutrinos will change to the electron type by the time they get to, okay, say, this detector after traveling 1,300 kilometers. Right. Now, another experiment which is also competing with Dune is, okay, called the Hyper-K experiment, right now being constructed in Japan. So in this case, again, okay, a very intense muon beam is produced, okay, by one of the national, okay, facility in Japan. They will shoot the beam towards, okay, the west side of Japan with a distance about, okay, 300 kilometers, and then they are going to build, okay, another underground cavern to house its 2 water detector. And because, okay, in order to measure, okay, say this, okay, phenomena, we'll need, okay, quite a bit of, okay, the data. So as a result, they are going to build 2 gigantic detectors. Each one is a 1/4 megaton. In order, okay, say, to do this measurement, and also there are some, okay, the Korean colleagues, okay, talking to the Japanese colleagues about, okay, mounting another detector in South Korea, so that will enhance the scientific capability of this experiment. Now, both Dune and Hyper-K are extremely complex, and it will take a long time to build. So, for instance, for the Hyper-K, even though okay, the experimental techniques they use is quite mature, because we have used this technique before. However, they still need a few years in order to get the underground cavern, and also some time to build these 2 gigantic detectors. So the hope is, towards the end of this decade, then they will be able to start doing the experiment. And then for Dune, which uses the very new experimental techniques, it will take some even longer time. So this experiment probably will start data taking about 2030 or so, and each experiment will take about 10 years to collect data in order to do some measurement. So therefore, coming back to what the Professor Chu said, a lot of the time we have to be patient. We cannot just rush and thinking in 3 or 5 years time, then we will get a lot of scientific result out. It doesn't work that way in reality. So to summarize, the take-home message, we have by studying neutrino oscillation is now we know neutrinos that have some very tiny mass. We still do not know the exact mass yet, and they can essentially change their identity as a function of time. And because of the discovery of the neutrino oscillation, now we have compelling reason to believe our so-called the standard model of particle physics is broken. There will be some new physics emerge in the future. So therefore, this is a very exciting time to do science. Thank you.
Thank you very much, Professor Luke, for this fantastic talk. So we have received many questions from the online participants, and I would like to start a Q&A with one of them. Do neutrino observatories have to be built underground to avoid interference, as in the case of the Kamioka Observatory? And how does the diabetes experiment fit into that category?
Well, this is a very good question. Indeed, every second we have the cosmic ray coming, raining down, and they do produce a lot of unwanted interaction in our detector. So therefore, in order for us to study neutrino interaction, which is very rare, then naturally we have to go underground. So then we use the mountain to shield all the cosmic rays. Now for diabetes, I show say a cartoon drawing showing we also need some shielding in order to cut down the interference of the cosmic ray.
Okay, thank you very much. Is there any questions from the participants on site?
I'd like to ask a not very scientific question. Those experiments you described are obviously absolutely massive in scale.
Yes.
So just say for the Daya Bay,
yes,
you had to build a 3-kilometer tunnel.
Yes.
So I'd just like to ask, basically, where do you get the money from?
That is a very, very good question.
And also, how do you manage the logistics because it must be quite specialized, presumably.
Indeed. I think that you asked a very, very excellent question. So in particle physics nowadays, certainly we tend to say build very massive and complex detectors that will require a lot of expertise. So that's also the reason why usually for the say a collaboration, we have collaborators with different kind of skill. For instance, for diabetes, actually besides physicists, we also have a group of chemists to help us to synthesize the liquid scintillator. On top of that, as you correctly pointed out, the detector is massive, and certainly physicists cannot handle the task. So we have a team of engineers and technicians to help. Now, regarding the first question, the civil construction usually is provided by the so-called host country. So that's also the reason I mentioned that even though the Hong Kong team decided not to do the experiment, but it's no way Hong Kong can afford that. As a matter of fact, I don't think the Hong Kong government will care anyway, right? So therefore, the only way we can really realize our dream is to convince the other people to join us. So in this case, the Institute for High Energy Physics in Beijing, we have friends there, so we talk to them, and they agree. Yes, this is something we should do together because the science is just too important. So once we come to this kind of agreement, then to make the story short, the central government decided yes, this is a very high priority scientific project for China. So therefore, they provide the funding to build the tunnels. As a matter of fact, the power plant, even though they are for business, however, they also provided us some money. And also, the Shenzhen government, embarrassingly enough, they, to me, that they also provide funding as well as the Guangdong, the provisional, the funding agency. They also provide funding, and then of course, besides, the civil construction, we also have to build the detectors. So in this case, then half of the money, came from the U.S. because, according to the international protocol, you may say, we cannot, provide U.S. taxpayers' money to build something, in China. So the only thing we can do is, to provide, detectors, and then the other half, coming from mainland China, Hong Kong, Taiwan, and also, some small portion from Czech Republic and also Russia. So this is usually how it works. Yeah.
Okay, due to the time constraint, let's accommodate one last question. Okay, I think there is a question from the online participant that is very relevant to the previous discussion.
Yeah.
So you mentioned it takes so many years and so many resources to
Yes.
Do this experimental observation for fundamental physics. So how do you know, like, we are on the right track in the process?
How we know we are? This is also a great good question. Well, I would say. Well, first of all, okay, this is very similar to, okay, say a Chinese saying. I apologize, okay, to say in Cantonese. 呢個係需要 okay 天時地利人和. So essentially, without luck, then it's very difficult, okay, to push, okay, say a project forward. Yeah. When do we know, okay, we are on the right track? This is really hard to tell. I mean, even for Daya Bay, actually, we have gone through a lot of, okay, say, ups and downs. And for a while, I can tell you, I was so depressed. By the time I got home, I say, that's the end of it. I better, okay, think of something else to do. But the other day, then all of a sudden, okay, I got some good news. Then we say, okay, now we can move forward. But with, okay, say backing from many, okay, say the places and also, okay, colleagues, then it will happen.
And when it happens, the reward is very big.
Well, put it this way, we never thought, okay, the doing Daya Bay is for any rewards, right? Essentially, all of us, okay, really wanted to know whether Theta 1.3 was 0 or non-zero, because okay, that was okay the most important question.
Yes, that's very nice. Let's thank Professor Luke and all the speakers of today again.
Thank you, Professor Luke and Dr. Dai. Thank you very much. And ladies and gentlemen, time flies and it is almost the end of this seminar. Once again, we'd like to express our gratitude to our distinguished speakers and also our moderator for hosting the section and also taking time off their busy schedule to make this seminar happen. Please give them another big round of applause. And I'm sure all of you have gained a lot from our speakers. On behalf of HKLF, I would like to thank everyone for joining us today at the seminar.